Hey folks, this is Major Jones here to talk to you about arithmetic circuits and the ALU that we're going to use for the computer that we're going to build over the next few lessons. It's called the HackALU because affectionately the computer is called the Hack CPU. So today we're not really going to learn any new concepts. We're just going to start applying the things that you already know about binary arithmetic and combinational logic here. So we're effectively going to take these two things and kind of like throw them in a little blender and do something really useful. All right. Last lesson we talked about the actual mechanics of how we do something like binary addition, and hopefully it's not a big stretch for you to realize that we can design a circuit that does this for us. So we're going to start by trying to build up to this device here that is an adder. In this case, it's a 4-bit adder. So you take two 4-bit numbers and then perform binary addition of those two numbers. And this, if we wanted to do it the sort of, kind of rigorous, straightforward way, right, we would have, potentially an 8-column truth table where we like specify what all of our like 5 output bits are. And that is absolutely a technique, but that's a big truth table. So what we're going to do is actually break this problem into kind of 2 component pieces. And if we look at the process of addition, what we realize is that there are really just 2 kind of operations that we need to perform. One of which is sometimes performed multiple times in a row. So the very basic thing we might do is say, well, the 2 numbers all the way on the right, all we need to do is take in 2 bits that are added together and then produce the sum and potentially a carry, right? You can see here I'm adding 0 and 1. The result of that is merely 1, so that becomes the sum, and I carry a 0. And so the symbol for this is right here. We call this a half adder because we don't need to worry about a bit being carried in, and we just have to have our 2 inputs here, A and B, to make that device. This is very straightforward combinational logic design problem. So I've left it blank here because I want you to be able to do it, right? Fill in the truth table for what should be the result here, that sum and carry, given these 2 values that I'm adding together. And then from that truth table, I want you to draw the circuit. All right. If we move kind of 1 column to the left in our addition, we realize that we need a slightly different device. It is still adding, but instead of just adding these little 2-bit numbers here, A and B, we need to account for potentially the fact that I might have a bit being carried in, right? We might have a bit carried over from the column to the right, so I have to account for that as well, although I'm still just generating 2 outputs, my sum and the carry out that might go into the next sort of column. So we call that the full adder because we are accounting for the fact that I might have a carry in bit. You can see the diagram right here. This is still a very straightforward combinational logic problem. The truth table is just a little bit larger because I have to account for not just the 2 values that I'm adding together, A and B, but also potentially a carry in bit. So I've also left that blank because I want you to be able to do it. So fill in the truth table here for the values that would go, that would be the results for the sum and the carry out if I'm trying to add these numbers together. And then I want you to build that circuit. All right. And now that with those 2 devices, we can take a look at our 4-bit adder and realize down here that, oh, to do 4-bit adding, or really any sort of multi-bit adding, I really need just at most a half adder all the way on the right-hand side to add the least significant bits together, and then I need as many full adders after that to add my 4 or my 8 or my 64-bit numbers. So we can compose this adder of just a series of full adders and half adders. And so that adder might look like this. What I want you to do is, I've kind of given you the structure. I want you to complete the circuit diagram here, right? Assuming the full adder and the half adders have, their components or the block diagrams are sort of as shown here. Connect them together to do full 4-bit adding. And you can refer to like the 4 bits of A as like A3 to A0, B3 to B0. And the sum is S3 to S0 with 1 little carry out bit potentially. That might be the result of carrying out of the last column all the way on the left. So annotate where those signals go and complete any little wires in here you need to complete the 4-bit adder. Okay, now that we have an adder, right, we can perform addition in binary using digital circuits. We're going to build on that to this thing called the HackALU. HackALU is short for Arithmetic and Logic Unit. So all we're doing really is we're saying, well, you know, addition is really useful. It might be very useful if I could take this adder and kind of choose whether I wanted to add A and B or perform the logical ANDing of A and B, right? That would be potentially a useful thing to do. So you can see here kind of the generic symbol for an HackALU. It looks like kind of a squashed V, and I think the reason is because I've got two inputs, A and B, that I'm combining into one output, C, and the operation is controlled by something like an operation code or something, right? And so you can see for a very simple HackALU, very simple arithmetic logic unit, I might say, well, let's treat A, B, and C, so the inputs and the outputs, as if they were signed 16-bit integers. And like I said, we'll say this HackALU can do one of two things. It can add A and B together, or it can do the logical ANDing of A and B. And so we just need a single bit. Our operation code just needs to be a single bit to kind of control which of those we are performing. And furthermore, the last thing that HackALUs do, which is really useful, is sort of report whether the result is 0 or if it's negative, or sometimes we'll check to see if the results overflowed because we were trying to add two really big numbers together or something like that. In this case, we'll just say, hey, we've got these two flags, 0 and negative, that tell us whether the result is of those qualities or not. Well, I've shown it here, right? But hopefully, you could already see in your head, okay, this is pretty simple, right? I just need something that adds A and B. I need something that ANDs A and B together, and to choose between one of two things to go to my output. It sounds like a multiplexer. So what I've got here is, a generic 16-bit adder that gets A and B, a 16-bit wide AND gate that will AND together the A and B numbers, and here my little opcode sort of just selects which one is which, right? If it's 0, then it's the result of the AND gate that goes to my output. And if it's a 1, it's the result of the adder that goes to my output. And then I'm not showing the combinational logic here, but the output might go through something to sort of detect whether it was 0 or 1, right? And these are signals that would indicate that result. Believe it or not, this is basically all we need to build a computer. At the heart of every computer is an HackALU that does the actual either arithmetic or logical operation on data. And that just happens, a couple billion times a second, and that's basically what makes your computer work. So this is kind of like our first stop on the process of building a computer, is having this little combinational logic unit that can do some useful arithmetic or logical operations for us. The HackALU that we're going to build, or that we're going to use in our computer that we're building up, is just a touch bit more complicated, right? You can see here the same structure. I've got two inputs, X and Y, one output. They're all 16 bits. I've got, in this case, 6 bits that control which operation is being performed, and the same 2 flags in the output, whether the result is 0 or if it's negative. Okay, so same format, we just have more bits to kind of control this thing, which means we get to do more stuff. So hopefully you saw in the reading the description for the HackALU, which looks like this. And my inputs, my controlling inputs are these 6 right here, and they're described in this table as being ZX is short for whether or not I allow the X input to pass, or whether I just replace it with a 0 value. NX is whether X is negated. So after I choose whether or not the X or a 0 value goes through, then I have the option of taking that value and negating it, right? Performing the logical not operator on that value. I have the same 2 options for the Z input, right? So down here, Y. My Y input, I can also choose to allow it to pass through, or replace it with a 0 value. And whichever one of those goes into my the next part of my HackALU, I have the option of negating that as well. And then the last 2 inputs here, F and NO, have to do with my output. So F selects which operation is performed, right? If F is true, then the output is the result of the A and the Y inputs. Or, if these were true, right, there might be like a 0 and the Y, or, the X and not Y, or something like that. If F is 0, then we do the logical ANDing. Okay, so just like our simple HackALU, right? I can do adding or ANDing with this thing. And then NO stands for negate output, right? So then the last thing I can do is after I've done my adding or my ANDing, I can also choose whether or not the result goes unaffected to the output or whether it gets negated first. And with these 6 control bits, I can do a whole heck of a lot of things, right? Let's scroll all the way down. Okay. So here's a table of some of the things that I can perform. It's actually not all of the things that I can perform with my ALU. And so we'll take a look at, for instance, this first row right here. All right. So a 1 in the ZX position means that whatever the value of my X input is, it gets replaced with a 0. A 0 in the NX position means I'm not negating it, right? So a 0 is goes into one of the inputs to my adder and my AND gate. I'm doing the same thing with my Y input. So I'm zeroing it out and then I'm not negating it. So the other input to either my AND gate or my adder is a 0. F being 1 means I select the add operation. So my output is the result of the X plus the Y, which were both 0. So it's 0 plus 0. That's my output. And I am not negating that, so that goes through unaffected. So this first line shows you how we might use our ALU to just emit a constant 0. That's actually useful, believe it or not, for many cases to sort of like make sure some part of our computer is sort of reset or cleared out. So this series of control bits will make my ALU emit a 0. Let's take a look at, this is probably another really good one here, right? Another simple one. Okay, so in this case, I am not zeroing my X value, so it goes through unaffected. I'm not negating it, so X is present on the inputs to either my adder or my ANDer. I'm not zeroing my Y, I'm not negating my Y, so that also goes through unaffected. F is still 1, so I'm using the add operation, so my output is the result of X plus Y unaffected, and I'm not negating the result, so my output is performing the add operation on both my X and my Y. So this is a super useful ALU in class, or I'll say at this point you might be able to sort of design this out. And I'll give you a little hint, right? Like, remember that choosing between one of 2 options kind of sounds like a multiplexer, right? So so you can probably design this. If not, we'll go over it in class. And our goal today is to sort of see how we can use this ALU to perform a whole bunch of useful operations on these 2 inputs, X and Y, and then we'll start using that to build up our computer, in the next few lessons. All right. So if you haven't yet, all right, go back and make sure to finish the design for these half adders, the full adders, the 4-bit adder, and take a crack at seeing if you can design the ALU. Hopefully at this point it makes sense how we might perform arithmetic operations in logic and how we might build a really useful combinational logic device called the ALU. That's all I got. I'll see you next time.